there's really two kinds of measurements you can make. There are exact numbers and there are inexact numbers. And this is not going to happen very often when you're making measurements. Exact measurements aren't made unless you can actually see the individual things that you're counting. Right? So if I have some pennies in my hand and I can put them on the table and count every single one, I know the exact number. There's really no uncertainty there. So when you can count individual things and you can see each individual thing, you can make a measurement that's exact. That should have infinite or unlimited significant figures associated with it. So you don't have to limit significant figures. If you're using an exact number, you don't need to use that number to limit significant figures at all in any calculation. Also, relationships that are definitions are exact values. So any metric conversion you make, like going from kilograms to grams, that's a definition. There's no uncertainty in how many grams are in a kilogram. It's an exact number based on what defines a gram and what defines a kilogram. So if there's no uncertainty there, there's unlimited or infinite SigFigs associated with that. And so when your calculator treats the number 1,000, it treats as if it's 1,000 point infinite number of zeros. That's actually a situation where your calculator is right, because if you're looking at 1,000 grams per kilogram or 12 things in a dozen, that's exact based on the definition. There's no uncertainty there. So if you can count individuals and you have an exact number, or if it's a definition you have an exact number, you don't have to worry about SigFigs when it comes to those values. They're not going to limit your SigFigs. But anything that's measured with some kind of instrument, like the balance in the back, could be a digital instrument. A digital instrument is nice because a digital instrument like the balances just gives you as many decimal places as it can measure, and no more, no less. So if you have 3.054 grams, then that's 3.054 grams. You don't know what comes after the 4 because the balance only gives you so much information that it's confident about. So it's pretty straightforward when it comes to making measurements on a digital device. Devices with graduations, with lines, and you've got to line something up, it's a little bit trickier, so we'll talk about that on another slide. Just to make sure we have down the idea of exact versus inexact, question 1.33 in the text says, indicate whether the following measurements are exact or not. So A is 50,247 tickets were sold for a sporting event. That's an exact number, right? They counted each individual ticket. There shouldn't be any uncertainty there. So the number 50,247 has unlimited SigFigs associated with it. Part B there says 750 milliliters of water used to make a birthday cake. 750 milliliters of water, is that an exact number? No. How do you measure that? You've got to get a graduate cylinder or some type of device with graduations. You've got to pour the water in until it's about 750. There's uncertainty associated with that. You don't know exactly what the volume is because the device could have uncertainty in it, and you're lining things up with your eyes. You know, the meniscus of that water might be a little above or a little below 750. So there's only so much certainty you can have based on eyeballing where that is on the graduation. Part D, 0.41 grams of oxygen was inhaled in each breath. That is an inexact measurement. Again, you'd have to measure that somehow with some device that's measuring grams. So if you're using a device to make a measurement, the device has limitations. You can't see each thing you're counting. You're using a device to do the counting for you. It's got limitations. It's introducing some uncertainty, and that's going to affect the significant figures that you have. So what happens when you are using a device? Well, this is a good example. I'm not sure why the textbook uses this. Weird picture of something that is a flash disk, whatever that is. But it does do a good job of illustrating the difference between using this device to measure the length of that object versus using this device. And this is really relevant to when we're measuring volumes today. So we have a variety of containers that you can pour liquid in and measure its volume. Well, ideally, you want to use a container that gives you the most information when you're measuring that volume. And that's going to be the device that has the most graduation on it. So this example illustrates that. So if I use this lesser device, when I'm making my measurement, I can tell if I'm measuring the length of this flash disk that it's somewhere between 2 and 3. Right, so I'm 100% confident about this 2. And it's definitely, I can tell between 2 and 3. So it's 2 point something. Do I have information about the first decimal place, the 5? Do I have any information about that decimal place? Or is it completely unknown? Well, I can kind of eyeball. I can see that with this ruler that the edge of the device goes up to about 2.5, right? It's not 2.1. It's not 2.9. So the first digit here after the decimal, the 0.5, is significant. Okay, the term significant doesn't mean I know it 100%. It just means it's significant because it's important. I have some information about it. So when you're when you're using a device with graduations to make a measurement, you want to include all the numbers that you have some information about. Anything that you're really certain about, plus 1 that is significant. Even if you had to do a little bit of guesswork on it, you still have some information about it. It is relevant, it is important, it is significant. So here maybe it looks more to you like it's 2.4. That's okay. You can write 2.4 because when you report a measurement, whoever reads that will recognize that there's not really 100% certainty in the last digit you record. There's maybe a little bit of uncertainty there, but you had some information, so it's at least close to what the value should be. It's important because we have some information about it. So with this ruler, at best, we can get 2 SigFigs. We have some information that it's about 2.5. Can we say 2.50? No, it could be 2.48 or something like that. We really can't say anything at all about the second decimal place, so we only have 2 SigFigs there. 1 decimal place of certainty. However, if I use a ruler with more graduations, then when I line it up, I can get more certainty. So if I look closely and I line this up real well, I can see now it's clearly between 2.4 and 2.5. So if I can see that it's between 2.4 and 2.5, then I can tell, because I have more graduations now, I can make 2 digits of 100% certainty and 1 digit that's somewhat of an estimate. So maybe it looks to you like maybe it's more than 2.47. That's fine if you want to write that. 2.46. You know if the 2 and the 4 are correct. The next digit is somewhat of an estimate, but you still have some information about it, so it's still important and significant. So if I were to take this value and do some calculations with it, it's better than taking the 2.5 and doing calculations with it. Because here I've got more SigFigs. It's not going to limit the SigFigs I have later out there to do my calculation. Questions about that? And so when you're measuring volume in a graduated cylinder, you want a graduated cylinder with as many graduations as possible. That way, when you see the meniscus for the liquid inside that cylinder, you look at the bottom of the meniscus, you can line it up, and you can make a measurement with more digits, more significant figures. You include all the digits you're certain about, plus 1 that's maybe a little bit of an estimate. That's what you're meant to include. Okay, so when it comes to SigFigs then, when you're making measurements, you've got to look at the device you're using and recognize how the device limits how many digits you can be certain about and report those digits. If you're reading numbers that someone else reported, though, you have to know the language, the conventions on how to read significant figures. So there are really 4 rules. The first rule is pretty straightforward. Any digit that's reported that's not a 0 is significant. So if you've got a bunch of non-zero digits, if they're writing the number, they wrote it because it's significant. That is an important digit or a significant digit. So when someone made this measurement, they have some information about the 1. They included it. It is significant, so I have 4 total significant digits in that measurement. If there's a 0 present and it comes between non-zero digits, then the 0 is significant. It wouldn't be there if it wasn't known to be a 0. So this has 3 including the 0, this has 4 including the 2 zeros. And so the first 2 rules are pretty straightforward. Again, these rules are based on the idea of communicating which numbers I actually have information about and which numbers I don't. The next rule, or rule number 3, says that if I have zeros present and they're to the left of the first non-zero digit, then they're not significant. Those are just placeholders. They're just there to show, for example, in this point 0.00001, the zeros are here just to show that the value is a small value. It's not 1. It's a tiny fraction of 1. It's 0.000001. So these zeros are not significant in themselves. They're just placeholders. And you can recognize that also if you were to convert that to scientific notation. It would be 1 times 10 to the negative 6. Right, so if I convert this to scientific notation, I have to move the decimal place 6 times. It would be 1 times 10 to the negative 6. That's one significant figure. The only digit I have certainty about there is the 1. I don't know what comes after the 1. So the key thing when you're looking at zeros is where are the zeros in relationship to the non-zero digits? Are they in between the non-zero digits? If so, they're always significant. Are they to the left of the non-zero digits? In that case, they're never significant. The trickiest one, though, is if they are to the right of non-zero digits. If your zeros are to the right of a non-zero digit, then they are significant if there's a decimal shown. The zeros do not have to be to the right of the decimal. They just have to be to the right of the non-zero digit. So in this case, these zeros are significant. Why are they there? If I didn't include them, and I just wrote 1.2, is that any different from 1.200? Not mathematically, but yes, it's different in terms of communicating digits I have certainty about. If I just write 1.2, that means when I made this measurement, I wasn't able to get any information about the next digit. But 1.200 says I do have information about what the next digit is. There's a difference in terms of what I'm trying to communicate. So that's the point with this rule. If you see a 0 after a non-zero digit, and there's a decimal anywhere shown, what they're communicating is that those are known to be zeros. They're not some other number. They're not just placeholders. We know they're zeros. We don't know what comes next, because next there's nothing shown, but we know those zeros are zeros. And then the last one has to do with if there's no decimal shown. In this case, it's ambiguous, meaning it's uncertain, meaning the person hasn't communicated properly about the number that they're reporting. Okay, so you shouldn't write numbers like this. If you have zeros to the right of a non-zero digit and there's no decimal shown, that's not the correct way to communicate. Because you haven't really communicated to me whether those zeros are significant or not. I don't know. There's some rules for significant figures that say if you put those zeros there, they're not significant. But if you put them there, they kind of look significant. So in this situation, if you want to report 100 and you want to communicate that those zeros are significant and that they're known to be zeros and it's pretty close to 100, it's not 150 or something, it's really 100, how would you report that those zeros are known to be zeros and that they are significant? How would you write that? There's two ways to do it. You could write 100 point. I think I heard someone say that. Right, so here I have applied Rule 4. I have zeros that are to the right of a non-zero digit, and I have a decimal somewhere. That's my way of communicating that those zeros are known to be zeros and not some other digit. The other way to do it would be to put it in scientific notation. These two mean the exact same thing. They mean the number 100. They mean I have certainty in the 1 and 2 zeros that come after that 1. Questions about that? What if I wanted to communicate the number 100 with only one significant figure? I'm sorry, not 2, 3. This is 3 SigFigs. if I want to communicate the number 100 with only one sig fig, the only way to write that is 1 times 10 to the second. There's only one way to communicate unambiguously with no uncertainty that I have the value 100 with only one significant figure, and that's to put it in scientific notation. Yes?
What would be the point of writing 100
The point would be is if you, let's say you're using like a beaker to measure volume, and the beaker only has graduations every 100 milliliters, or maybe there are no graduations at all, and you just pour some water in there and you eyeball it, it looks like it's about 100 milliliters. I mean, this type of measurement would not be done very often, and it would not be smart to do it, if that's the point I'm making. I agree. It wouldn't be smart to make a measurement of 100 milliliters or something with only one significant figure, because it's way easier to grab a different measuring device and measure that with more certainty and get more significant figures from it. So it's not really advisable to do that, but you know, if maybe this was the answer you had from some calculation, and you made some other measurement, the best you could do with that other measurement was to get one significant figure, and you had to plug that into a calculation, and so your answer was only able to have one significant figure. If you had to report that with one significant figure, that would be the way you would have to do it. Go ahead.
If you had 1.0 times 10 to the second?
That would be 2 sig figs. So in that case, that's a good question. So if you had the number 100, this came from maybe a calculation that you did, and the numbers you're plugging into the calculation were limiting you to 2 significant figures in the end. Then you would report that as 1.0 times 10 to the second, because you would only have certainty in the first 2 digits and not the second 0 there. Any questions about the rules? I mean, these rules might seem kind of arbitrary, but we have to come up with some convention so that when we write numbers down, we can communicate about which digits we have actual certainty about. And so that's the convention that scientists use. So look at this example. Go through this kind of quick. How many significant figures are in each one of these? So 443 centimeters, 3 sig figs. That's pretty easy. No zeros involved. 3 numbers, 3 sig figs. B, 15.03 grams. 4, right? The zeros in between the non-zero digits. So it is significant. And then C, 0.0356 kilograms. 3. Yeah, almost all of you got the ones on the quiz. So I know that you already have a pretty strong idea of how to do that even before you came in. Any questions about those? Okay, I encourage you to look at 1.36. Make sure that you're up with your scientific notation skills. If you want me to check those over, since that is an even number, the answer is not in the back of the book, I'd be happy to look over your answers there and make sure you're on the right track with that. All right, so we talked about this already, but let's go over it again. So if I have to add or subtract values that I've measured, the answer I get is going to be limited by how much certainty I had to start with. Right? I can't claim a bunch of certainty in numbers if I'm getting those numbers from uncertain numbers. And so, as we said, with adding and subtracting, what we do is we line up the decimal place, and then we look at each column that we have numbers in, and we decide which columns we have some certainty about and which columns we don't. And so the key column here that we do not have certainty about is this last column. Right? The number 102.50 has 5 sig figs, but none of those sig figs appears in this third decimal place column, and I have no idea what the number should be there. So I can't add a totally unknown number to a 1 and claim that the answer is a 1. So that means that since I only have 2 digits after the decimal place of certainty, or 2 columns of certainty past the decimal place, I can only have 2 columns of certainty past the decimal place in my answer. And I have to use the first insignificant or unknown digit to round. And since it's less than a 5, I wouldn't round up, and I would have 102.73 there as my answer. What if I were going to add something with scientific notation? And this was like the quiz question, and that was the one that most people didn't quite get. So let's look at that. In this case, I've got to really kind of first take this number in scientific notation and expand it back to the normal notation to see where the decimal is, so I can do what I just did here, which is to line up the decimal place and analyze the columns. So 1.1 times 10 to the third is 1,100. So here I'm putting these two zeros in there as placeholders, but I know they're not significant. I've got to keep that in mind. Right? This number came from one that only had two significant figures, so only these two these two places or columns have significant figures. Then I'm going to add that to 345 in my calculator, and I'm going to get 1445. So the 345 is fine. I've got certainty in all these columns. But in the 1,100, that only had two SigFigs. I don't have certainty in these columns, so I've got to block them out. And since this digit is a 4, I'm not going to round up, but the two digits I have, I still have to communicate that as being 1,400, not 14. So I need scientific notation there. Questions about that? Yes?
So that was a 5 or any greater number we would have to round up.
Correct.
So we can really use it
Correct.
otherwise.
Yep. Good question. Other questions? Yeah, we always use whatever the first digit is that is not significant to round.
You said that was adding? It's 2.
What?
1,100, 3 plus 3 and 4 and 5.
Yeah. Right, I didn't put the plus sign there, but yeah, I was adding. All right, so that's the rule for adding and subtracting. And this is the rule for multiplying and dividing. And I'll tell you that probably 80% of students, that's a really rough estimate, will mix these rules up and will begin to apply the multiplying and dividing rule to situations where you're adding and subtracting. I'm telling you that now, so maybe you can avoid that happening to you. Because as we go through calculations in this class, the majority of them will be multiplying and dividing. And you'll get really used to using the rule for multiplying and dividing all the time. And then your mind will just keep applying that rule, and it will start applying it to situations where you're adding and subtracting. And then you'll get the wrong SigFigs. Right? So make sure you remember the rules for adding and subtracting are different from the rules for multiplying and dividing. You've got to apply them appropriately. So for multiplying and dividing, it's pretty straightforward. You've got two numbers you need to multiply or divide, or more numbers. Whichever one has the fewest, that's the one with the least amount of certainty. So when I multiply or divide with that number, I can't claim a bunch of certainty that I don't really have in my answer, because it's limited based on how many digits of certainty I had for the numbers I plugged in. So I just have to figure out how many significant figures that the one with the fewest has, and apply that number of significant figures to the answer. So I would limit that to 11. I would get rid of the 0.2154. I would use the 2 to round, but I'm not rounding up because it's a small number, and so I just have 11 there as my answer. I can't report more than 2 SigFigs if I'm multiplying and dividing, and I had to plug something in that only had 2 SigFigs. Here I'm dividing. Same rule though. So here I've got 4 SigFigs with this number, 5 with the next. So the one with the fewest is 4. So I would apply those 4 SigFigs to this number. Again, these zeros don't count. Students make this mistake a lot too. They would say, well, I've got 4 SigFigs, so I'll just start from the far left and pick the first 4 digits. If I do that and I write 0.037, that's only 2 SigFigs. Now I've lost information that I should have. I don't want to lose information, and I don't want to claim false information. I just want to report correctly that I've got 4 SigFigs of information. So since those 2 zeros aren't significant, it's these 4 digits that are the significant ones. In this case, since the next digit is a 5 or larger, I've got to use that to round up, which is why I end up with a 3 there.
Because I'm having trouble seeing like difference or an area for error between the
Yeah, there are lots of examples where if you apply the wrong rule, you won't get the right number of SigFigs. So I don't think any of the examples we did actually show that, but I can make one up. So let's say I had 1.25 times 10 to the 4th plus 345. This number has 3 SigFigs. Actually, that's not going to work. Let's do this. This number has 2 SigFigs. So if I were multiplying or dividing these, my answer would end up with 2 SigFigs. But if I'm adding and subtracting, I still have to line up the decimal places. So the 1.25 times 10 to the 4th is 12,500. And I'm going to add that to 34. So I end up with 12534. But these zeros are not significant, so I've got to get rid of these columns. So that means my answer should be 1.25 times 10 to the 4th. So I end up with 3 SigFigs, even though the one with the fewest had only 2. So there are cases where if you apply the multiplying dividing rule to a situation where you're adding and subtracting, you might end up with too few or too many SigFigs. You really have to line those up to make sure you get the right number of SigFigs. Sometimes you might get the right answer by mistake, and then that could reinforce the wrong idea that you've used the right rule in the situation when you haven't. That's unfortunate. All right, any other questions so far? All right, so in the case when you have an exact number, like a metric conversion, don't use that to limit any significant figures in your calculation. So, for example, or if you have things you can count. I've got 3 pennies. I can count exactly 3 pennies. Each one has a mass of 2.5 grams. So how would I figure out the total mass? Well, if I've got 3 and each has a mass of 2.5, I'd multiply that together, right? So I'd multiply the 3 pennies times the mass of 2.5 each. So if I incorrectly identify 3 pennies as having 1 SigFig, then I would limit my answer to 1 SigFig. That's not correct. Because the number 3 is just a single digit. It looks like only 1 SigFig, but it comes from recognizing that there are exactly 3 pennies. I don't have any uncertainty there. It's not like I have 1 digit of certainty when I measure 3 pennies. I have unlimited certainty because I know it's exactly 3 pennies. I can see each individual penny. So this exact number has unlimited SigFigs. If I multiply a number with unlimited or infinite SigFigs by a number with 2 SigFigs, the whole diffused is 2. So my answer should have 2 SigFigs. Any questions about that? One other point about SigFigs is if you have to do a multi-step calculation, you shouldn't round until the end. You want to keep a few extra SigFigs and then look back at how your SigFigs were limited and only round one time at the very end of the calculation. So this example illustrates why that is. Don't round after each step. So let's say this is a really simple example where I'm multiplying these 3 numbers together. If you were to do this in your calculator, you'd probably just multiply them all together in one step, round to 3 SigFigs at the end, and you'd have your answer. And that would be fine. That would be perfectly correct. But sometimes when you're doing multiple steps, sometimes students will multiply 2 things together. They'll take the answer to that. Then they'll multiply it by the 3rd thing, and that will give them their final answer. So what we're saying here is, if you're going to multiply these 2 first, don't round down to 3 SigFigs, and then multiply by the 3rd, and then round again. Because every time you round, you might run into a situation where if you do multiple steps, you might be rounding up every time at the end, and then your number gets magnified incorrectly and it becomes larger than it should be. Or vice versa, if you're rounding down every time, your number gets smaller than it should be. So in this case, if I were to round after every step, so I multiply the first 2 numbers together, I get 30.9. I want to keep more digits than that, than my calculator gives me. At least 1 extra digit, because I don't want to round till the very end. Because if I do round to 3 SigFigs here and then carry that through to the next calculation, my answer becomes 65.2 with 3 SigFigs. That's not the right answer. if I keep that extra digit and carry that through, then only round once at the very end of 3 sig figs, then I actually get the correct answer. It's only a slight difference, but that last digit difference could make the difference if it were an important situation. So if you have multiple steps, only round at the end of those steps. So let's just look at a couple examples here, a couple more examples. I'm going to try to save more time for lab, so I'm probably not going to do each one of these, but let's just do this first one here. 317.5 milliliters plus 0.675 milliliters. One other point is, if you're adding or subtracting two numbers, they have to have the same units. You can't add 5 milliliters plus 6 grams and get an answer that makes any sense. That doesn't make any sense. If you're going to add things together, they have to have the same units. They have to be measuring the same thing. So in this case, I'm adding these milliliters together. If I did it on my calculator, I would get 318.175. But I realize that I don't have any information about these two positions, so those columns have to go away. Although I am going to use the 7 to round, so I end up with 318.2 milliliters as my answer. So in this case, that's another illustration of your question. I had only 3 sig figs here, but I am entitled to 4 sig figs in my answer because I've lined things up and I recognize I have 4 columns worth of information. Questions about that one? Okay. The rest of these are worked out in the textbook. You can check those out. I suggest that you try to work them out on your own. Maybe check your answers with what's in the textbook and worked example 1.5. Make sure you're on track with this. If you're not, and you have questions about them, let me know. They're actually also worked out on here. All right, one last topic we need to get through before we talk about lab today, and that is the difference between accuracy and precision and what those two terms mean. So in the English language, they're kind of used interchangeably, but in science, they actually have different meanings. So the definition of accuracy is it's a measurement. It's a way of communicating how close a measurement is to the actual value for that measurement. Right. So if you're measuring in the lab the density of your unknown metal, and you get 6.5 grams per milliliter. But the actual unknown metal you had really has a density of 8.9 grams per milliliter. That's not very accurate. So when you go to measure the density of your unknown, can you tell whether that measurement is accurate? Not really. If you don't know what the real value should be, you have nothing to compare your measurement to. You don't know how accurate it is. Okay, so measuring accuracy requires for you to know what the real value is that you should be getting when you're making your measurement. If you don't know that, you can't say anything about how accurate your measurement is. So the analogy that the book uses is throwing trash in a garbage can. Your target is to hit the garbage can. If you hit it, then you have accurate technique and you're getting it in there. In the garbage can, you're hitting that target, right? So when you make a measurement, it should be a certain value to be correct. And if you know what that value is and it matches, then you know that it's accurate. Precision, though, is different because precision requires you to have multiple measurements to see how they agree with one another. So in this lab experiment, when you're measuring the density for your unknown metal, you're not going to be able to say how accurate your measurements are. But if you take multiple measurements, you will be able to determine how precise your technique is. If you're measuring the density of this metal and you get 6.5 grams per milliliter in one measurement and you get 2.8 grams per milliliter in another measurement, those two do not agree well with one another. That means something is going wrong with your measurement. You're not getting the same value every time you repeat the experiment. That's poor precision or imprecise measurement. So precision is about whether you're doing it the same way every time. Right? So this first picture represents both precision and accuracy. I'm hitting my target every time, that's accurate. Plus, I'm doing it the same way every time, so it goes to the same spot every time, that's precision. What does the second picture represent? Precision without accuracy. Right? So if I do it the same exact way every time, I could get the same number every time. That doesn't mean the number is right. It doesn't mean I'm hitting my target. Right? So if you measure your density, 6.5 grams per milliliter, 6.6 grams per milliliter, 6.3 grams per milliliter, that shows precision. You're getting the same measurement every time. It doesn't mean it's right, though. You have to know what the real value should be to know if it's accurate, even though it's precise. And then here I have neither accuracy nor precision. Same example here, except here it's a little bit more of a scientific example. Here I'm measuring the mass of an aspirin tablet. If I know what the mass should be, then I look at my students measuring the mass, I can determine how accurate their measurements are. When you're comparing accuracy, you should be comparing your average value, if you made multiple measurements, your average of those measurements with the true value to determine how accurate it is. So it is possible to be accurate without being precise. If I'm not precise, that means when I make the measurements, my measurements are all over the place. They're not in agreement with one another. However, by chance, I could average those measurements that vary wildly together, and the average of those measurements could actually match the real value for what I've been trying to measure. So I could be accurate even though I'm not precise. Chances are that's not going to be the case, though. So if you're making a bunch of measurements and they don't agree with one another, like this student here in the middle, the blue column, their measurements vary pretty significantly from one another. It's pretty unlikely that if they average those together, they're going to get an accurate measurement. So you want your measurements to be precise. Usually that's a good sign that you have accuracy, but not always. That's what the problem with this first student. So somehow this first student's making the measurement the same way every time, but they're not getting the correct value. So even though the technique is precise, they're not measuring accurately. Then the third student is good. All their measurements are in close agreement, and the average of those measurements is close to what the real value should be, so that's both precise and accurate.